Many thanks to the invitation from the Congress Committee of Materials Science and Nanotechnology. Today my topic will focus on the title of an aqueous zinc-ion battery type pressure sensor. I'm Jie Luo from Suzhou Institute of Nano-Tech and Nano-Bionics, Chinese Academy of Sciences. Today, the content of my presentation will be divided into three parts. First is the background, and the second is the sodium dioxide carbonized cotton-based SIB and sensor. And the third is the fiber type SIB sensor. With the huge market demands for hembeans on the intelligent electronic products and the rapid development of wearable technology, intelligent products like smartwatch and ring and belts and clothes, etc., can not only monitor people's heart rhythm, sleeping quality, movements, and other physiological signals and joint motions to help people manage their health conditions. However, among these smart electronics products, energy storage systems are one of the most important parts that could impact the lifetime and the work states. In addition, the high cost, safety issues, and limited nature source seriously limit the common used lithium polymer batteries. Although it has high energy intensity and received many attentions, as you see, like the smart band or watch work with small power. However, another fairly negligible point is the comfortability. As you can see many struggle marks on people's skin. Anyway, it's very important to and meaningful to develop novel candidates with big safety, low cost, and environmentally benign characters. Fortunately, the aqueous zinc-ion batteries received many concerns because of its super volume capacity, safety, and stability, as well as reversibility in aqueous media. Among the metal ions, in our previous achievements, fiber-based electrodes like fiber type SIB were systematically investigated for improving the zinc anodes stability and their properties. And then we fabricate the intelligent fabric through special processes to wherein these fiber batteries and devices can achieve charging and sensing and energy storage. For example, sodium dioxide, one material that was usually used in battery cathode materials, was fabricated through a simple route of carbonization following hydrosome process. And the sodium dioxide presents a root structure with high aspect ratio of 30 and big length of 600 nanometers. After 7-digit structure assemblation with sodium dioxide cotton cathode, gel electrolyte, zinc anode, 2D zinc-ion battery was obtained. It presents a distinct capacitive property and good rate capability, as well as long cycle life over 5,000 with 88.7% residual capacity. In addition to the battery materials, sodium dioxide carbonized cotton also can be used as sensing materials due to its brilliant mechanical property and the dielectric feature. Thus, we stuck two pieces of sodium dioxide with face-to-face direction to prepare a sensor device. For this flexible piezoresistive sensor, the working mechanism is very simple. After loading a low pressure on the surface, the long aspect ratio of sodium dioxide will touch each other, and at the same time, the rich channels will be built as the loading increases. Once the release of the loading, the connection between the volume dioxide will be separated, and then the sensor will go back to the original state. Sensitivity is a very important factor for evaluating sensor performance. In our experiment, the sensor device fabricated by volume dioxide carbon cotton materials present good sensitivity with as high as 7.12, which is for about 40 times higher than the sensor device with only carbonized cotton. And also, especially our sensor device can monitor a wide range of pressure from 0 par to 120 kilopar. Additionally, this device displays brilliant sensing repeatability and virus pressure. It also present show rapid response recovery rate. For example, at 500 par, it reached 12 microseconds and 8 microseconds respectively. And it also can adapt to different frequency and same pressure, and maintains over 5,000 cycle life without any significant degradation. As a proof of concept, our device can also be used for body monitoring, such as joint motions, physiological signals, tests. When bending fingers, it can present different current and different bending angles. Other actions like fisting, saying words, and blowing can also be recognized clearly. Finally, a fantastic practical application was demonstrated as well. We assembled these two devices in series. Here you can see a LED light. It can be partially controlled by press the sensor device. Obviously, although the highlights of volume dioxide carbonized cotton materials can not only be used as energy storage materials, but also sensor materials. Several obvious drawbacks, such as it needs two devices connected in series and low pressure detector range, big size, and complex circuits, seriously limited their practical applications. Certain groups proposed one body strategy to construct a novel AZIB sensor device. Um, However, the low potential and the lean water-hard transfer channels and can't prepare irregular devices limited their application size. Thus, in order to solve these problems, we developed a new concept of developing fiber-type ZIB sensors with high potential and due to the 1D structure character and one body model design. So the device has a smaller volume and rich water-hard transfer channels and can prepare irregular devices with a wider application size. However, the interfacial stability issues and the lifespan issues can still be seriously concerned. The popular brusher blue and its anglers received many concerts in the field of energy storage. Zinc brusher blue is proposed and synthesized. As you can see, the beautiful cubic zinc brusher blue uniformly distributed on the carbon nanotube fiber, and which illustrate beautiful, highly reversible CV curves and the potential as high as 1.9 volts, which is very useful for improving the sensor sensitivity. For the sensor device, another important part is the electrolyte. In this project, we try to synthesize hydrogel electrolyte through simplified EITRP to construct a low dispersity and well-defined architecture polymer for preparing gel electrolyte. And we have obtained several valent works cooperated with Padua University and University of Cordoba, Spain. In addition to the cathode and hydrogel electrolyte, another important step is the fiber device preparation. As you can see, a homemade machine was used to construct a one-body coaxial structure device. This device presents high sensitivity and different pressure, and it also presents rapid response recovery rate. Despite these advantages, for the long-time cycle life, the multi-level interface stability need more worries. In conclusion, several aspects such as the cathode materials interface issue and the hydrogel electrolyte as well as the sensing mechanism also need further investigation. And especially the device integration and application also need the help from experienced team. Welcome somebody to offer some ideas to help us to solve these problems. In the end, I really want to share some works about functional materials and integrated devices from our group, such as the sensors and also the fiber electrode materials. We have rich experience in the aspect of electrolyte polymerization, and we also have many cooperation with Padua University, especially on the simplified EITRP technology. And finally, many thanks to the cooperation groups, and welcome you to cooperate and join us. Thank you. Thank you very much. Thank you for your attention.